here we have an equation that we're trying to solve using both part A and part B. Drop my pen. When we solve using part A, or even if the directions just said solve or solve for all solutions or all radian solutions, you really still have to do part A in order to do part B. So I'm just kind of explicitly stating both of them. So when we solve something like this, I actually told you guys that it reminded me of number 3 on I gave you guys 8 examples that were on like that little transition lesson from 13 to 14. Does anyone have what number 3 was in front of them? Can you read it off to me? I forget off the top of my head. I meant to have it out, but.
You said 3.
Yeah, 3. Either, anyone, go ahead.
1 minus sine squared theta over 1 minus cosine squared theta equals cotangent squared theta.
No, it wasn't that one. It was like the handwritten, it had X's in it. Or like a letter. It was like a variable, no trig was in it. It was the one where we factored a few examples. We had to use a least common denominator in this one. Do you remember? Let me look.
Miss Thomas, which one are you talking about?
It was on that transition from 13 to 14 worksheet.
I think it was 4 over y squared plus 3 equals 8 over y.
Yes. So it was kind of like that example right there. So this one here, we ended up multiplying, if you guys remember, we multiplied everything by the least common denominator, which was y squared. And it ended up turning into a quadratic type, and we solved from there. So similarly, I'm just going to kind of play with this one here. What if I did 2y plus 1 equals 1 over y? What I did was I kind of just did a little substituting to this and rewrote it over here. What did I do? They're really the same exact structure, these two. What did I do to create this equation right over here?
Substituted cosecant for 1 over sine.
That's one thing. We substituted cosecant for 1 over sine. And I also substituted sine with what?
Y.
Y, exactly. So if I were to do this the same way we started this, I would multiply everything by y. And it would clean up and I would get 2y squared plus 1y or y equals, and what would I get over here? 1, right? Y over y. So I would get this, get it equal to 0, factor and solve. So we're going to do that right here. So some people might want to rewrite cosecant into 1 over sine first. So think of the strategies and techniques that you guys used when you were verifying trig identities. Like you wanted all of the trig to kind of be matching each other, or you wanted to identify some of the identities, reciprocal, quotient, or Pythagorean. You wanted to get it down to as few trig equations or expressions as possible, types. So I'm going to go here and I'm going to replace cosecant theta with 1 over sine theta. That's my reciprocal identity. And then you could do it from here, or some of you might in your head think of it this way and right away know that you could just multiply by sine theta, or like I said, if you did it that way. Either way, if you multiply by sine theta, what do we get for the next line? 2 sine squared theta plus, and remember to multiply by everyone. I feel like when we're doing these problems, sometimes your brain drifts off and you like stop distributing and you just start copying. So just careful there. Plus sine theta equals 1 over sine times sine is?
Sine squared theta.
1 over sine times sine.
1.
1. Yeah, it's just 1. Because it's sine over 1 times 1 over sine. Reduce, reduce, everything's gone. So it's just a 1. Now it's a quadratic type. Anytime we solve any polynomial that's a degree bigger than 1. Polynomials with a degree of 1 are just linear expressions or equations. So solving those, we don't have to get it equal to 0 to solve. we want to get everything with a higher degree equal to 0 first, because we'll factor into linears and then set each linear equal to 0 and solve. We want to solve linear equations, not jumbo higher degree polynomials. So we're going to get this equal to 0. So we move 1 to this side with subtraction. 2 sine squared theta plus, that's technically a 1 sine theta equals, what am I doing? Minus 1 equals 0, right over there. And then we're going to do what on this cutie patootie over here? What are we going to do? Go ahead, Alice. What are we going to do now?
I have a question.
Mm-hmm.
What if you factored out a sign before you subtracted one?
Okay, that is something that is very common, and that's why I always say, like, it only works factoring when we get it equal to this happy 0. I draw this stupid doofy 0 over here, you know, because the name of the property is actually called the zero product property. If I had, I'm just going to make up like a basic example, like x squared plus x equals 2. Yeah, I guess. Hopefully I'm not messing up in my head. If you tried kind of your idea, right? X times x plus 1 equals 2. Then x equals 2. This is bad that I'm showing, okay? X plus 1 equals 2. Subtract 1, x equals 1. We got 2 answers. If I plug these answers back in, do they still work? Are these solutions of that equation? So if we plug 2 in, 2 squared plus 2, I get 4 plus 2, I get 6. That does not equal 2. Failure. And then if I plug in 1, coincidentally 1 does work. That doesn't always happen, okay? The reason it doesn't work is because if I say this equals 2 and this equals 2, if I try to say both of these equal 2, well, then their product equals 4, not 2. However, if you have something factored, x squared plus x equals 0, x times x plus 1 equals 0, there's nothing wrong with saying x equals 0 and or x plus 1 equals 0, because if that and that equals 0, when you multiply them, it still equals 0. All right. Now, will it work sometimes coincidentally to get you where you need to be? Maybe coincidentally, but you want to get it equal to 0. The name of the property is the zero product property. It is designed that when we're solving anything that's written as a product of many factors, 1 factor, 2 factors, 3 factors, if it's equal to 0, each of those factors can equal 0. And that's what gets us all of our solutions. So you always want to make sure, really important, that we get it equal to 0 first. Okay. But I know a lot of people will do that because, like, I feel like we notice opportunities to factor and you're like, ooh, GCF. You know, you want to take it out so bad, but hold your horses, you know, get that little smiley face first. Okay. Get a little happy nose. Any other questions before I move on? I see hands up. I just want to see do we have questions or are these answers for what to do? It's okay if they're answers, but all right. I don't think question because I think you would have shouted out. So go ahead, Lincoln, what would I do in the next step?
You factor by multiplying the first and last.
Sure. We're going to do 2 times -1 AC and we get -2. So we need something that multiplies to give us -2 and adds to give us
1.
1. Good. So what multiplies to give us -2? Well, it's got to be 2 and 1, but it has to add to give us 1. So which one's positive and negative? And we could split it up. Now, if I do grouping, that's the longer way of doing it. If I do grouping, that's fine. Do any of you factor by just jumping right into your parentheses? Are we able to do that? Or do most of you write it out and show the grouping?
Yeah, I do that.
You do it the short way? Okay. Anyone else do it the short way? Like a thumbs up if you do sometimes.
Miss Thomas, what is the short way?
So the short way is like how I learned how to factor when I was in like 8th grade or whenever, I don't know, whenever you learn how to factor, where my teacher literally taught us how to factor by saying, you know, you guess and you check in your head and figure it out.
Yeah, that's the way that I do it as well.
right? So does that work? Yeah, for some people. Other people though are like more like, I need a method. Don't give me this guess and check like abstract craziness. Please, I want a method that works every time. So async method is a method. It works every time. It is truly what you are actually doing when you do guess and check in your head. It just formalizes it. Okay, you are thinking like my outer and inner need to be this, right? My first, last, blah, blah, blah. Now this one's easy for guess and check because we're dealing with 2, which is a prime number, and 1, which isn't prime by definition, because prime numbers have 2 distinct factors, 1 and themselves. 1 only has 1. So it's easier because the numbers aren't crazy. What first multiplies to give me 2 sine squared? Well, I would do 2 sine theta and sine theta. 1, I don't really have many options, 1 and 1. Then I kind of think it through. Outer, inner. Outer is 2 sine theta, inner is sine theta. I need a positive 1. So my outer positive 2 and my inner negative 1. Then I'm done factoring. If you factor with AC method, beautiful, keep doing that if you like it. It's reliable. When I started teaching, I remember one of the first things that I taught, I was like, wait, I'm not going to explain to these kids like you guess and check in your head, you know, like how do I factor? Like what's the right way? So, you know, AC method, and the way I kind of show it is a little bit more detailed, but nitty gritty, but some people need that. Okay. And I find myself actually using that more often than not whenever the numbers are not prime, because like, I don't want to guess and check. Sometimes it just takes too long. Okay. From here, we set each factor equal to 0. Again, 0 product property. 2 sine theta equals 0. 2 sine theta equals 1, or minus 1 equals 0 before. Divide by 2. Sine of theta equals 1/2. And now this should be kind of user-friendly, you know, like not scary. And then here, sine theta plus 1 equals 0. And sine theta equals -1. Are you guys thinking like you're getting better at figuring these out in your head? Like you could picture where on the circle sine is -1. Can you picture on the circle now where sine equals 1/2? Can you like give a thumbs up or the hands up, hand icon, whatever the heck it's called, if you think you are getting better at it? You don't have to be a master, but like, you know, you notice you're improving. You can imagine it in your head more. Okay, pretty good amount. Good. So it's not for nothing, all of the insane going over it, because it's paying off. So here, for this first one, sine of theta equals 1/2. If we were only doing part A, what 2, I give away that it's 2, what 2 angles are we going to put? So somebody give me one. I'm just going to pick people with their hands up, okay? KF, what's one of them?
pi/6.
Sure, quadrant 1, pi/6, sine is positive there. Jason, what's another one?
5/6.
Good, 5pi/6, that's in quadrant 2, sine is positive there too, because we go up into those places and that sine is positive. What about when sine of theta equals -1? Again, just part A. The sine of theta equals -1 where? Can you tell me? Go ahead, Makai.
3pi/2.
Nice, 3pi/2. So part A, those are the answers, part A. Now, what about part B? Part B. What do I have to do to each of these answers to finish it up and find all of our solutions? So we had, I'm just going to draw a little happy cloud over here for part B answers. Part B, finding all solutions. So theta equals, and I'm just going to go over here, pi/6 was one of them, 5pi/6 was another one, and 3pi/2 is another one. What do we just do in a nutshell? Go ahead, Zareen. What do I do for these?
You can just add plus 2πk or n, where n is an element in the set of integers.
Right, we could write it out just here. And then if you want one time at the end, you just put n is an integer, an element in the set of integers. You could put that once on your homework and just apply to all examples, and you could be done right there. Did anybody?
Honest?
Yeah, go ahead.
So what you just wrote, like the NEZ, I know that's not what it is, but like that's just what it looks like.
Nez, yeah.
So yeah, what is that, and like when do you write it? Because I was a little bit confused about that.
Okay, so that is basically defining what n is. Like we're introducing this new letter in our answer, right? So when we introduce this new letter, I have to explain what it is. I can't let n equal anything. It has to equal an integer because like what if I plugged in 0.5? Okay, that's just a random number. What's 2 pi times 0.5 going to give me?
Sorry, I was just copying down the notes.
No,
You
it's
said it
okay.
one more time?
2 pi, what's 2 pi times 0.5? Or 1/2?
Just pi.
Pi. And what's pi over 6 plus pi?
7 pi over 6.
Is that a solution to this equation? Will 7 pi over 6 make it true?
Yeah.
What
no,
does,
no, it won't because it's not an integer.
well, 7 pi over 6 as an angle, it makes sine equal negative 1/2. I want it to equal like positive 1/2. But to get another answer that will make it true, pi over 6, I can't add pi because it's not going to put me overlapping pi over 6. But by saying n easy, what we're actually writing is, I just want to squeeze this somewhere. I'm going to go over here. That the n that I'm using is an element of the set of integers, z, this z with the extra line in it, is the set of integers. So dot, 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 -2, -1, 0, 1, 2, dot, 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 close off our set bracket. So that's saying we're adding full amounts of 2 pi. We're adding a whole 2 pi once, or we're adding a whole 2 pi twice, or 3 times,
Yeah,
or
that makes sense.
subtracting it. So I actually recorded myself last class with period 3, where I went on to answer this question that you're basically asking me. So what does this actually do, right? So I'll post this for you guys later, and I'll put it underneath this video when I post this one. But if I got answers like that, what's happening? So what I did for them, and I explained this in the video, I explained how we have all these answers that go on forever. When we solve between 0 and 2 pi, we found this pink answer and the yellow answer, 3 pi over 4 and 5 pi over 4. But I want every single answer in that part of the graph as it goes on and on forever. So if I just take this pink answer and keep adding 2 pi, boom, I'll hit that one. Boom, I'll hit that one, and so on. So I actually worked it out with plugging in some negative numbers underneath and got some other answers. But we wouldn't do this and list all of our answers. We'll be listing for the rest of our lives, you know? We'll just be like going forever and ever. So it's even like if I asked you like, what's the circumference of a circle with radius 1? And you're like, okay, 2 pi r is my formula. If the radius is 1, it's 2 pi. And then you went and you tried to multiply and find the decimal, and I told you to be exact, you'd be writing for the rest of your life. So we invented the pi symbol, and we're like, don't you worry, this symbol, this like shortcut, it includes everybody. You know, just like a square root of 2, that's an irrational number. It goes on forever. It never ends. We're not going to write that. So what do we write? We invented this little symbol, and we say like, we just write it like this. It's everything. Okay. So,
Thank you.
yeah. So that's what that means. Am I on the right thing? Okay. So that will, like I said, I'll share that little video, and that'll encompass all of your answers right there. Any other questions or concerns? Alex question, or Zareen or Makai, Jason, or just your hands are up for participating? Anything? We're good? Or?
Are we going to go over more problems, Ms.
Yeah.
Thomas, from this worksheet?
Yeah, we're going to do more. I just want to end this video before, but I want to make sure I get any questions on this
Okay.
example in this video. So Alice or Bela, do you have questions on this example?
I have a question on a different example.
Okay, so I'll end this video here. So if you are able to do this example for yourself, you could record and your own records and give it thumbs up. And if you don't think you could do this example by yourself or one like it in the future, put a thumbs down so we know we need more practice, okay?